when a business loses money, we say it is in the red. When it makes money, it is in the black. The phrase is so worn that nobody hears the colors anymore. It comes from the ledgers of European accountants, who wrote losses in red ink to make them leap off the page. 2,000 years ago, and half a world away, mathematicians in China were also using red and black to mark the difference between gain and loss, not in ink, but in little sticks of bamboo laid out on a table. And they had it the other way round. Red rods were the positive quantities. Black rods were the negatives, the debts, the amounts below nothing. Those black rods are the first negative numbers in the history of the world. They appear, without ceremony, in a book compiled in China around the 1st century of the Common Era, appear not as a discovery announced with trumpets, not as a philosophical crisis, not as a scandal requiring anyone to be thrown off a ship, but as a rule. Here is how you add them. Here is how you subtract them. Now back to the grain problem. Meanwhile, in Europe, 15 centuries later, the great Italian algebraists were still calling such quantities fictitious. Descartes called the negative roots of an equation false roots. Pascal is reported to have thought that anyone who imagined you could subtract 4 from 0 was simply confused. Well into the 18th century, working mathematicians were publishing arguments that negative numbers could not really exist because, as one of them put it, how can something be less than nothing? The same object. Routine in one civilization, an offense against reason in another, for 1,000 years and more. That is the puzzle this chapter is really about, and the answer to it will tell us something important about the whole shape of this book. Because we have been watching mathematics manufacture monsters, the unspeakable diagonal, the forbidden infinite, and treating those monsters as though they were simply out there, waiting to horrify whoever tripped over them. They are not. What counts as impossible depends entirely on what you have built your mathematics out of, period. The Greeks made monsters that the Chinese never met, and the reason is not that one people were cleverer. It is that they laid their foundations in different material. Start with the book. Its name is the Jiazhang Suanshu, the 9 chapters on the mathematical art, and it is to Chinese mathematics roughly what Euclid's Elements is to the West. The canonical text, studied, memorized, commented upon, and argued over for the better part of 2,000 years. But it is not remotely the same kind of book, and the difference is worth dwelling on. Euclid, as we saw, has a single architecture, and apparently a single architect. He starts from nothing, declares his assumptions, and builds upward in one unbroken chain of deduction. It is a cathedral, designed, load-bearing, all of a piece. The 9 chapters is a coral reef. Nobody wrote it. It accumulated over centuries, out of older material assembled and re-edited by hands whose names are lost, reaching something like its final form under the Han Dynasty around 2,000 years ago. There is no author to have anecdotes about. There are no axioms. There is no first principle, no quod erat demonstrandum, no cathedral. What there is, instead, is 246 problems, and they are problems about the actual running of a state and a farm. How much land is in this field? How much grain do you get when you mill this much millet, and at what rate do you exchange it for rice? How should a tax burden be shared fairly among villages at different distances from the capital, given that the ones farther away must pay more in transport? How many cubic feet of earth must be moved to build this dike, and how many man-days will that take? How deep is the water if a reed sticking out of a pond bends over, so that its tip just touches the surface a certain distance away? Read that list and you might think, recipes again. Babylon all over again, worked examples, specific numbers, no why. That was the honest verdict on the mathematics of Chapter 2, and the reflex is to apply it here. Do not. It is the standard story, and it is too simple, and the 9 chapters is the place where it breaks down. Because attached to these problems are not just answers, but procedures, methods, stated in general terms and detached from the particular numbers of the example. A rule you can carry away. And a couple of centuries after the book took shape, a mathematician named Lu Hui sat down to write a commentary on it. And what he wrote is not a set of hints. It is a body of justification, arguments for why the procedures work, built out of dissection and rearrangement, cutting figures into pieces and showing that the pieces must fit. He is not proving things the way Euclid proves them, from declared axioms. He is proving them the way a person proves something to another person who is genuinely paying attention, by making the truth visible. So there were at least two ways to be rigorous in the ancient world, and only one of them came from Athens. Hold on to that, because when we get to the 20th century and start asking what a proof actually is, what it is for, whether a computer can produce one, whether a proof no human can read is a proof at all, this will not be an idle question. Now the equipment, because in China the equipment shaped the mathematics more than anywhere else in this book. Chinese calculators did not compute on paper. They computed on a board, a table, a mat, a ruled surface, using small rods of bamboo, ivory, or bone a few inches long, carried in a bundle. To write a number, you laid the rods out in a column of the grid. 1 through 5 were simply that many rods laid side by side. For 6 through 9, you laid a single rod crosswise on top to stand for 5, and added the extras beneath, so 8 is 1 crosswise rod plus 3. And then the columns did exactly what our columns do. The rightmost column is units, the next is tens, the next is hundreds. Move a numeral one place to the left and it means 10 times as much, which is to say, place value. Real, decimal, positional place value, the thing the Egyptians never had, the Greeks never had, the Romans never had, and the Babylonians had only in base 60 and only imperfectly. The Chinese had it in base 10 and had it very early. They even solved, in an ingenious physical way, the problem that had dogged Babylon. Remember the trouble. With no zero, how do you tell an empty column from a column you simply forgot? The Chinese answer was to rotate the numerals. In the units column, the tens column, all the alternating columns, rods were laid one way. In the columns between, they were laid the other way, turned 90 degrees. A number in the tens place looked visibly different from the same number in the units place. And an empty column was simply an empty patch of table, obvious, unmistakable, because the rods on either side of it were oriented in ways that told you exactly which house you were standing in. Notice what that means. The Chinese had a zero. It was a hole in the world, a gap in the rods, a place where your hand found nothing. It worked perfectly, and because it worked perfectly, nobody needed to give it a name. File that away. It is going to matter enormously in the next chapter. Now to the showpiece. Chapter 8 of the 9 chapters, called Fengqing, which means something like rectangular arrays. The problems in it look innocent. Here is the first one, in essence. You have 3 grades of grain, top, medium, and low quality. 3 bundles of top grade, 2 of medium, and 1 of low yield, a certain measure. 2 of top, 3 of medium, 1 of low yield, a slightly smaller measure. 1 of top, 2 of medium, 3 of low yield, less again. What does a single bundle of each grade yield? This is a system of 3 equations and 3 unknowns. And if you have ever met one in school, you know the feeling. Substitute this into that, rearrange, hunt for a way in. It is fiddly, and it gets rapidly worse as the number of unknowns grows. The 9 chapters does not fiddle. It gives a procedure, mechanical, repeatable, and guaranteed to work. And here is what you do. Lay out the numbers on the counting board as a rectangular block. 1 column of rods for each of the 3 recipes, stripped of all their words. No bundles, no top grade, no grain at all. Just the naked numbers in a grid, arranged so that position tells you what each one means. Take a moment on that because it is a genuinely deep move. A grid of numbers, detached from the things they describe, manipulated by rules that pay no attention to what the numbers stand for. That object has a name in modern mathematics. It is a matrix. And the whole enormous apparatus of linear algebra, which now underlies computer graphics, quantum mechanics, economic modeling, structural engineering, and every neural network on Earth, is the study of what you can do to such grids. It begins here, on a table, in rods. And what the procedure does to the grid is this. Suppose one column tells you about a mixture with 3 bundles of top-grade grain, and another tells you about a mixture with 2. Scale the whole first column up and the whole second column up until they agree on the top-grade grain. Then subtract 1 column from the other, entry by entry. The top-grade grain cancels out completely. It is gone. You have destroyed one unknown and are left with a simpler problem. Do it again to eliminate the second unknown, and again until one column contains a single number that tells you one answer outright. Then walk back up the chain, substituting what you now know into the columns above, until every quantity has fallen out. That method is called Gaussian elimination. It is taught in every linear algebra course in the world. It is named after Carl Friedrich Gauss, who used it in Germany in the early 19th century, and it is one of the most used computational procedures in existence. Right now, as you read the sentence, some machine somewhere is running it. It is in the 9 chapters, complete 1800 years earlier. And here, right here, in the middle of that procedure, is where the negative numbers walk in. Watch what happens when you subtract one column from another. Sometimes the number you are subtracting is bigger than the number you are subtracting it from. Not because anyone was being philosophical. Not because someone wondered whether nothingness could be exceeded. Simply because the arithmetic of elimination throws you there over and over as a matter of course. 3 minus 5. You are halfway through a calculation, the machine demands an answer, and there is no way to continue without one. You could stop and declare the problem malformed. Europe, in effect, did exactly that for a millennium and a half, reorganizing equations, insisting on setups where the awkward case never arose, treating a negative result as a sign that you had asked a stupid question. The 9 chapters does not stop. It reaches for a second color of rod. Right there in Chapter 8, embedded in the elimination procedure where it is needed, sits the Sing-Fu Shu, the rule of the positive and the negative. Red rods for one, black for the other. And then the rules, stated flatly, in the tone of someone explaining how to carry a digit. When the signs are the same, subtract the values. When they differ, add them. And here is what the sign of the result must be. Every rule correct. Every rule still on the board in a classroom today. There is no discussion of what a negative quantity is. No defense of its existence, no apology, no acknowledgement that anyone might find it strange. The greatest metaphysical scandal in the history of arithmetic gets, in its first written appearance, roughly the same treatment as instructions for a fraction. So why? Why was this the easiest thing in the world in China and an intellectual crisis in Europe? I want to offer you the explanation I find most persuasive while being clear that historians argue about it in that I'm giving you an interpretation, not a fact. Think about what Greek mathematics was made of. After the disaster of the diagonal, the Greeks had rebuilt their subject on magnitude, on lengths, areas, volumes, the geometry of actual figures. When a Greek mathematician wrote what we would call an equation, he was talking about a square built on a line and a rectangle laid beside it, and how much room they take up. That is the foundation. That is the floor. And now ask the forbidden question in that language. What is a length less than nothing? What is a square with negative area? The question is not difficult. It is meaningless, like asking what color Tuesday is. There is no such object. There could not be such an object, and the reason is not squeamishness. It follows directly from what the Greeks had decided mathematics was about. Their foundation could not hold the thought. Now think about what Chinese mathematics was made of. Not magnitude. Procedure, a set of physical operations performed on rods arranged in a grid. The question is not, what is this number a length of? The question is, what do I do next? And within that frame, a negative number is not a strange object at all. It is a rod of a different color, sitting in a column, obeying rules. It doesn't have to be anything. It has to work. There is a broader cultural point often made here, that a tradition already comfortable with paired complementary opposites, light and dark, yin and yang, would find a matched pair of opposed quantities natural, rather than alarming. It is a suggestive thought and it may well be right, but it is the kind of explanation that is very easy to reach for and very hard to test. So I offer it lightly. The structural point I will stand behind. The monster is created by the house. Not by the mathematics, and certainly not by nature. Every impossibility in this book is impossible relative to a set of foundations, and change the foundations and it may walk in through the front door and hang up its coat. The Greeks built a beautiful house that could not contain the negative, and then spent centuries insisting the negative was a beast. The Chinese built a different house, and the same creature came in and made itself useful, and nobody looked up from the grain problem. Keep that in your pocket. When we get to imaginary numbers, and to infinities that come in different sizes, and finally, to statements that are true but unprovable, the temptation will be to say, How could anyone have thought that was impossible? The answer, every time, is because of the house they were standing in. Including us. Including now. Let me give Lu Hui his due, because he is one of the great mathematicians of the ancient world, and hardly anyone outside China has heard of him. He wrote his commentary in 263 CE, in a fractured and violent period after the Han collapse, and it is so good that for most of the last 17 centuries, the 9 chapters has been read through it. Text and commentary bound together, inseparable, like a poem and its best translation. Where the original states a procedure, Lu Hui asks why it works, and answers. His characteristic tool is dissection. Take a solid, cut it into pieces. Show that the pieces reassemble into something whose volume you already know. He handles the awkward wedge-shaped solids that come up in earthworks by chopping them into standard blocks and pyramids, and demonstrating that the count must come out right. It is proof by rearrangement, visual, physical, and completely convincing. And then he attacks the circle. Remember Archimedes, 1 chapter ago, trapping pi between inscribed and circumscribed polygons with 96 sides. Lu Hui, with no knowledge of that work whatsoever, does the same thing. He starts with the hexagon inside a circle, doubles it to 12 sides, then 24, 48, 96, computing the area at each stage, watching the polygon swell toward the curve. He gets 3.14. Then he keeps going, out to a polygon of 3,072 sides, and arrives at a value equivalent to 3.1416. But the thing I want you to hear is not the number. It is what he wrote about the method. He says, in effect, the finer you cut, the less is lost. Cut and cut again until you cannot cut any further, and then the polygon and the circle coincide, and nothing has been lost at all. That is a description of a limit. It is the idea at the heart of calculus, stated plainly in the 3rd century, by a man on the other side of the world from anyone who had ever heard of Archimedes or Zeno or Aristotle's ban on the completed infinite. 2 civilizations in total isolation walked up to the same door. Neither opened it. But listen to how honestly Lu Hui handled the place where he got stuck. He tried to find the volume of a sphere. He built a beautiful piece of machinery for it, a solid formed by intersecting 2 cylinders at right angles, which he called the box lid, a shape that holds the sphere snugly inside it. And he understood that if he could measure the box lid, he could measure the sphere. And he could not do it. So he wrote that down. He explains what he tried, admits he cannot finish, says he fears to guess where he cannot demonstrate, and leaves the problem for someone wiser who may come later. Someone did. Around 200 years afterward, a mathematician named Zhu Jing finished it, using the box lid exactly as Lu Hui had set it up, by means of a principle he stated in general form. If 2 solids have the same height n, at every level their cross-sections have equal area, then the solids have equal volume. That principle is now called Cavalieri principle, after an Italian mathematician of the 17th century. It was written down in China around 1100 years before Cavalieri was born. There is a relay race here that ran for 2 centuries, between men who never met, conducted entirely through a book. Lu Hui put down a tool and said I could not use this. Perhaps you can. And someone picked it up. I find that a more moving image of what mathematics is than any story about a bath. Zhu Jing's father was Zhu Changzi, and he deserves a paragraph of his own. In the 5th century, using rods on a board, working within a polygon doubling scheme of the kind Lu Hui had pioneered, Zhu Changzi computed that pi lies between 3.1415926 and 3.1415927. 7 correct decimal places. To get them, he would have had to work with polygons of something like 24,000 sides, extracting square roots of numbers running to many digits, by hand, with sticks, without algebraic notation, without decimals as we write them, without a single error anywhere in the chain, because one slip anywhere kills the whole computation. That bracket stood as the most accurate value of pi on Earth for roughly 900 years. Nobody in any civilization beat it until a Persian astronomer at Samarkand in the 15th century. He also produced a rational approximation, 355 divided by 113, which is a small miracle of a fraction. It is correct to 6 decimal places, and there is no better approximation to pi with a denominator under 30,000. It is easy to remember too. Write the odd numbers in doubled pairs. 113,355. Split them down the middle and put the second half over the first. The book in which he explained his methods was called, with lovely modesty, Method of Interpolation. It was lost. What we know of how he did it, we know mostly from other people's references. The tradition did not stop there. It peaked, in fact, much later. The 13th century in China produced a burst of mathematics as impressive as anything happening anywhere in the world at the time. Qin Jiuxiao worked out a general method for solving systems of remainder problems. Find a number that leaves this remainder when divided by that, and that remainder when divided by this, which is why the result is called the Chinese remainder theorem to this day, and it is fundamental to modern cryptography. He also gave a numerical technique for solving high-degree polynomial equations that is essentially identical to a method published in England by William Horner in 1819. Yang Hui, around 1261, wrote out a triangular array of numbers in which each entry is the sum of the two above it, the pattern that generates the coefficients you get when you multiply out a binomial over and over. It is called Pascal's triangle. Pascal was born in 1623. And Yang Hui himself did not claim it. He says he is reproducing a method from an earlier Chinese mathematician, Jia Xian, who worked around 1050, nearly 600 years early and openly credited to somebody earlier still. Zhu Shiji, in 1303, published a work whose title translates as The Jade Mirror of the Four Unknowns, handling systems of equations and four separate unknowns with a positional notation on the counting board, genuine, sophisticated, symbolic in-effect algebra. And then, over the following century or two, this whole tradition faded. The counting rods were displaced by the abacus, which is faster for commercial arithmetic, but far worse for algebra, because the abacus cannot hold a matrix, a rectangular array of numbers, the way a table full of rods can. You gain speed and lose the grid. The civil service examinations, the engine that determined who studied what, shifted their emphasis. Texts went out of print and were lost. By the time Jesuit missionaries arrived in the 17th century and helped translate Euclid into Chinese, some Chinese scholars encountering advanced mathematics were meeting it, in part, as something foreign. While sitting a few hundred miles from where much of it had been done first, in books nobody had reprinted. Historians have argued for a century about why. The British biochemist and historian Joseph Needham, who spent his life documenting the astonishing depth of Chinese science and technology, posed the question so sharply that it now bears his name. Given so long and so commanding a head start, why did the scientific revolution happen in Europe? Answers have been proposed involving institutions, commerce, competition between rival states, the structure of the examination system, the relationship between craftsmen and scholars, and the sheer contingency of history. None commands agreement, and I am not going to pretend to settle it in a paragraph. But I will say what the question is not about. It is not about capacity. Anyone who tells you that some peoples are mathematical and others are not has not read the 9 chapters. One last thing, and it is the thread into the next chapter. We are still learning what these people knew. In 1983, archaeologists opened a tomb in Hubei province, sealed around 186 BCE, and found among the grave goods a bundle of 200 bamboo strips covered in writing. It turned out to be a mathematical text, problems, procedures, fractions, proportions, older than the 9 chapters and utterly unknown to scholarship until it came out of the ground. Like the palimpsest at the end of the last chapter, it is a reminder that the past we describe is the past that happened to survive. There is no reason to think we have the best of it. We have the durable of it. And now, the gap. The Chinese counting board had a 0, a real, working, positional 0, a blank patch of table where the rods were not. It did its job flawlessly for 2,000 years. But it was a place, not a thing. There was no symbol for it because there was nothing to symbolize. You cannot write down an absence of rods. You can only fail to put any rods there. And because it was never a symbol, it was never an object. And because it was never an object, nobody ever asked it a question. Nobody ever said, what happens if I add this to a number? What happens if I divide by it? To ask that, someone had to take the emptiness off the board and give it a name. Southwest, then across the Himalayas, to a civilization whose mathematicians were as bold with number as any people who have ever lived, where the emptiness got a name and rules and a place in the line of the counting numbers, and where somebody finally looked at nothing and saw something.